Hello everyone, so I'm back with my NMR part 3 video. As if you have not watched the previous two, please go back to my channel and watch the part 1 and part 2 to learn the basics of NMR, which is needed for mainly in research. I would say I will make a separate series on NMR for the theoretical aspects, but this series I am doing mainly to uh, analyze the signals, proton NMR signals, which is needed for research. So let's get started. Let me share the screen. So as if you do not know about myself, you can check my LinkedIn profile, Google Scholar, and ResearchGate profile, and you can check details of my research area. So let's get started. So how to make samples for NMR experiment? This is pretty simple. I think most of you know it, but I want to mention precisely the techniques which will help you to make a very good solutions. So first, what thing do I do? I just take a pinch of sample with a clean spatula. Be very careful. Your glasswares and spatula, whatever you use for your experiment, it should be very clean. NMR give signals for any impurity too. So please be careful that you do not take a dirty spatula or a dirty glassware. So for solubility test, what do? You take a pinch of sample. Your sample is precious, so you will not take a lot of sample. You just take a pinch. I would say zero point 0.1 milligram or something like that. And you take the NMR solvent. You will have a series of solvent in your lab, so you just take any one of them and with a glass pipette and add dropwise to see whether that pinch is soluble or not. So for this, one thing I want to mention that you will always not prefer to do the solubility test in a bunch of samples, so you can just have an idea like which sample may solubilize it. You generally purify your sample through column chromatography. So if your sample makes a zero point 0.5 RF in ethyl acetate hexane, I'm talking about a lower percentage of ethyl acetate hexane, like 50% ethyl acetate hexane, not more than that. In that case, your sample is usually soluble in cadmium, in CdCl3, chloroform D, and if your column chromatographic technique uses a solvent of like methanol DCM or higher percentage of ethyl acetate hexane, like more than 50% ethyl acetate, in that case your sample is generally not soluble in CdCl3. In that case you have to try methanol D, or like if your sample is not soluble in any of them, then you have to try the other solvents like DMSO. So I have used different type of solvents. These are the two thumb rules I have usually find the match, but they will not match 100% every time, so you just have to uh, test the solubility. Okay, so next, your if your sample is not soluble in any of the solvents, suppose you have tried CdCl3, you have tried methanol D, you have tried DMSO. Most of the samples are soluble in DMSO. But if your sample is not soluble in any of them, then you should try the following techniques. Try to warm your sample. slightly in water bath. uh, because we know that a slight rise in temperature increases its solubility. But be sure that do not overheat the sample, because your sample may melt, and that will just we do not want our sample to melt, right? So you can try this technique. You can try to warm your sample slightly within the solution and in a water bath, and you may see that your sample is now soluble. So if this technique doesn't work, you can try to sonicate or vortex your sample for some time. Sometimes this technique too work. Like you can see your sparingly soluble sample is now making a good clear solution. And sometimes I have seen this works very much. You can add some inorganic salt like potassium carbonate and vortex them together, and this technique works sometime too. And obviously you can try a different solvent like D2O, like acetone D, etc. Like if your sample is not soluble in any of the solvents after trying all these techniques, then you just have to work with your sparingly soluble sample, and you have to take your NMR very quickly. Okay, so another point I want to mention that usually I have seen that 5 to 7 gram of sample is good to get a good NMR. And usually I make solution in zero point 0.5 to 0.7 ml of NMR solvent. We do not want to use a lot of solvent because these solvents are very expensive. Okay, so point three, once you have made your solution, you just transfer your solution in a clean NMR tube. Be very careful, use a clean NMR tube. Otherwise, you will get all of the impurity peaks in your NMR, which you do not want. And do not forget to label your NMR tube. Otherwise, when you take NMR of like 10 samples, you are just, oh, what sample is that? So do not forget to label, okay? And always put a lid on the NMR tube. Caution, NMR tubes are very fragile, so handle them very carefully. And one more trick I would want to say, if you have less amount of sample, you just give more scans in the experiment. Usually we do 10 to 12 scans for a normal proton NMR, but if you have like 2 milligram of sample, then I use like sometimes 120, sometimes 150 scans. This helps to get a good NMR. If your sample, as I mentioned previously, is sparingly soluble in your in the solvent, and you can see like the some solids are there but some clear solution is there, try to take the NMR very very quickly before the solid completely precipitates out. Okay, so these are the few techniques which I have found very useful to get a good NMR. So, okay, now let's get started with the practice NMR. Like now I will show you one by one NMR of few compounds which I have made in my lab, and I have taken those NMR, and I will show you how does the NMR look like, and I'll show you how to predict the NMR from the structures. So let's get started. So this is our practice NMR 1. You can see the structure over here. This is a very simple structure. I had made this compound in my lab. And so you can see this NMR here. I'm sorry. Oops. So this is how do you do analyze the NMR? So let me first count the total number of aromatic protons. 1, 2, 3, 4, 5. Okay, so there are 5 aromatic protons, and then there will be 2 protons over here, There will be two protons over here and two protons over here and one proton attached to this carbon. So there are one, two, three, four different type of aliphatic protons, and there are five aromatic protons in the structure. So how do you do analyze this? So there is an option to integrate. I have mentioned in my previous videos that you will have an option to integrate in the NMR software. So we select this region. I have also mentioned the chemical shifts for aromatic and aliphatic carbons. So usually the chemical shifts of aromatic carbons are around this region, uh, from 6 to 8. So I definitely know that these peaks are for the aromatic carbons, sorry, aromatic protons. So what do I do here? I know there are five protons, aromatic protons in my structure, so I'll integrate this as 5. So I think I didn't integrate this as a reference. I integrated this peak because I knew that my structure uh, has these four type of aliphatic protons, of which this particular structure, these protons 3, it has a chemical shift around 4. I knew that from my previous experiences. So I integrated this proton as 2. So this is for 2 carbon atoms, 2 protons attached to the carbon, which is marked as uh, sorry, this is for 1. So I knew this, that this protons has a chemical shift of 4.1 or something. I knew it from my previous experiments, so I integrated these as 2. So and then I let integrate the others. So what do I do when I analyze NMR? I just take any of them as reference which I know completely this is the chemical particular chemical shift for this proton. So usually from my previous experiences, I know one of them, at least one of them I know, that this proton corresponds to like which chemical shift. So in this case I think I knew this one, these protons attached to the carbons, I knew that it has a chemical shift of 4.1. So I integrated it as 2, and then I integrated the others, and I get this as 1.1, I get this as 2.18, and this 2.7, and this is 3.17. Now let me rule out the solvent residual peaks, which I have already mentioned in my video number 2, I guess. So I already mentioned that you will always get the solvent residual peaks. So in this case, I have used cadmium CdCl3, chloroform D. So CdCl3 has solvent residual peaks around 0, 1.5 and 7.1. I know that, and you can check from the table in my second video. So these are not the protons characteristics for my compound. So you have to rule out these peaks, this, and one of these. Okay, so sometimes these protons, the solvent protons, they are not very prominent. Sometimes I do not see them. If like I have used very little amount of solvent, sometimes I do not see them, or I see a very small peak. In this case, I see this peak. So this, and one of these will be for the CDCl3, and the others, let me uh, try to match with the other protons. So this also I know that it has a chemical shift around 4.5. So let's check, this is 1.1. So obviously this is for this proton, and then there is 3 and 2 left. So 2 will be for 3 protons. So this is 2.7. So definitely this is for 2, and the other, this is the 3. I think it would be for which one? This one, yeah, this will be 3. So what do I do here? And let's match the aromatic protons. 1, 2, 3, 4, 5. So there will be 5 aromatic protons. It is 4.66. Usually you will not get like um a full integer, like you will not get 4 or 5, you will get something point like that. And you have to assume, if you get more than 4.5, then it is close to 5. If it is less than 4.5, then this is close to 4 usually. So one of these peaks, which chemical shift I am very sure of, I just integrate that as a reference, and I integrate the other protons, and I rule out the solvent residual peaks, and I try to assign the other peaks from these integral proton values. Okay. And if I do not know any of these chemical shift values, if I have not made this before, I do not know anything about the structure, then I just want try to integrate the protons over the aromatic region, because I know the aromatic protons, they will definitely come between 6 and 8. So I just know that I count the number of aromatic protons, and then integrate all of the protons over the aromatic region, uh, and I put a value corresponding to the aromatic protons, and then I integrate the other and try to match with my structure. Okay, so let's go to another practice, NMR. So this is another structure. So let's check how many types of protons are present over here. So this is type 1, 2, 3, 4. So there are total 4 type of aliphatic protons, and there will be 1, 2, 4, 5, 1, 2, 3, 4. So there are 4 aromatic protons present here. So in this case, I think I had integrated this as 3. I knew this proton, these two. This is an CH3. I knew that this has a, chemical shift around 3.9. So I have integrated these as 3. You can see the proton number is 3 here, and I have integrated the other protons correspondingly, and you can see this is a point 0.8, that means this is 1, 1, and 1, and this is 8.55, that is 9. So how many protons are here? 1, 2, 3. 3 into 3, that means 9 protons are present over here. So this peak is for this tertiary butyl group, a big peak of 9 protons. And this peak usually comes around 4.1. So this is for this, and these two peaks come uh, like they comes as 1 and 1. They do not come together, they come separately with like 2 protons. So it comes around 3. So these are the 2 protons for the protons attached to these 3. Okay, so how many aromatic protons are here? 1, 2, 3, 4. So you can see it is 4.3. So this is also matching. So this NMR confirms that we have this compound. Let's go to another practice NMR. So from this structure, again, let's see uh, how many types of protons are present here. This 1, 2, and 3. And there is also carboxylic acid. So this proton may not appear all the time. Sometimes it appears, sometimes it doesn't appear. So we will mainly focus at these aliphatic protons and aromatic protons. So as I already you have seen in the previous practice NMR, this comes around 4.2 or something. So you can see this is 4.1 and corresponding to one proton, and then this 3, this comes around 3.8. So you can see this 3.8, this is integrated for 3 protons, so this is corresponds to this 3. And then these 2 I have already mentioned, it comes as 2 different protons, so you can see 1 and 1. So these are corresponding to these 2. And now let's check how many aromatic protons are there. 1, 2, 3, 4. So there are total 4 aromatic protons. And now you can see 4.8. So which is more like close to 5. So this may happen due to this CdCl3 solvent, because this solvent has a residual peak over here. So it may come, the solvent residual peak may come in this region. Okay, so let's go to another practice NMR. So from this structure, you can see there are two different type of aliphatic protons present over here. And so, and how many aromatic protons are there? 1, 2, 3, 4, 5, 6, 7, 8. So you can see these aromatic protons in this region from 7 to 8. We have integrated this as 8. And then we get this 1 for one proton, and this corresponds to this. And then you will get another peak at around 3. This corresponds to this 2. And this is also the methanol solvent. So methanol has solvent residual peaks around 3.3 and 4.9. So these are the solvent peaks. Okay, so this is how we try to analyze the NMR structure we get uh, after making our compounds. We are always very curious whether we have made our compound or not. We check mass and we check NMR, and then we are confirmed that okay, we got our compound which we are trying to make. Okay, so I'll discuss more practice NMRs, and the more practice NMRs you see, and you can practice by yourself when you take your sample. Okay, so this is enough for today. So do not forget to like, share, and subscribe. And you are welcome to post any query in the comment section. I'll try my best to answer all of them. Okay. Thank you. Thank you so much.